Please join me in welcoming to the Distinctive Voices podium, Dr. Krysta Svore.
Well, good evening. Thank you all for coming this evening to learn a little bit more about an area that I'm extremely passionate about and very excited to see actually come into fruition. I'm going to talk about quantum computing and how this is truly going to revolutionize what it means to compute, how we compute today, the problems we can solve today, and the problems we can't solve today. Those problems will be transformed by a quantum computer. So let's jump in. Now, many of you know about computers, but did you know this was the first computer on record? So the first computer that we can look back and trace back to actually dates back to 100 BC. And many of you have probably heard about analog versus digital devices, right? This would be an analog device. It definitely wasn't quite error corrected how we do that today. It wasn't fully fault tolerant, but it was hard to drop out of your pocket like your cell phone. So pretty robust. But since this mechanism, we've made a lot of strides in computation. We can look to Babbage's difference engine in the 1800s, right? The ability to actually compute things on a machine, calculations, log tables, and so on. But this doesn't look exactly like our machines today, right? We then had the ENIAC in the 1940s. Of course, many of you know that this machine was quite important during the war. But this really, you can point to the ENIAC as one of the first programmable computers, right? It actually, you could ask it to do different programs, different problems, solve different problems. And programmable is something that's important when we think about quantum computing. We want it to be able to solve a variety of problems, no matter what problem we think of in the future that we want to ask the quantum computer to solve. We want to be able to program that into the device. So the ENIAC, being one of the first programmable computers, is quite an important step in our history of computation. More recently, in 2013, for example, this was the fastest supercomputer in the world coming out of China, the Tianhe 2. And here, when we think about supercomputing, we think of special purpose problems running on these supercomputers. And, they can be very, very fast. They have a lot of memory. But what's fascinating is if you've heard about Moore's law, which essentially talks about the scaling of the number of transistors on our chip, and it's actually paired with cost. But for today, let's just think about the number of transistors doubling roughly every year and a half. That Moore's law says that you double that transistor rate every 18 months. Even if Moore's law continues, there are some problems that we will never be able to solve on these types of digital machines, right? Whether it's your supercomputer, your cell phone, or your laptop, something that's based on a transistor that's digital in that sense and not taking advantage of another type of principle. Maybe that's quantum mechanics, maybe that's DNA. But those machines will not be able to solve certain problems efficiently, even if they got bigger and bigger to post-exascale in size. So we have to turn to a different type of computing, right? A paradigm shift in computing to solve some of the world's unsolvable problems. So we want to do that with a quantum computer. And that's what I'm going to tell you a little bit more about this evening. Now, Microsoft, that's my home base up in Seattle, in Redmond. And here's my manager, my boss. This is Todd Holmdahl. And this fall, Microsoft announced that we were entering this race in a bigger way than we had been. But in fact, Microsoft has been invested in quantum computing since the late 90s. And we've been thinking about how would you actually build a type of quantum computer that could be more reliable and more efficient and better in terms of resource savings and scalability and fault tolerance. And so we work on a type of qubit that I'll tell you a little bit about this evening And then I want to tell you about why we're so excited about quantum computing in general. Why do we want a quantum computer? And again, Microsoft, we've really expanded our team in the last few months to have a broader system-wide, full system approach to building and realizing a quantum computer and the algorithms that you're going to run on it. So a little history of where we've come from. This is Michael Friedman. Michael Friedman is a Fields medalist. He's a topologist, a mathematician, and in the last 17 years, he's also become a condensed matter physicist through the Microsoft quantum computing program. So Mike joined Microsoft in the late 90s, and with him, he brought his expertise in topology. At the time, there was also another very famous physicist that some of you may know. He actually resides in California, up at Caltech, Alexei Kitaev. And Kitaev and Friedman got together and started talking about physics and math and topology. And this led to the discovery and the invention of a different type of what we call a quantum bit, a qubit, a different way to store information quantum mechanically. And we call it a topological qubit in honor of the fact that topology actually plays a role, and Mike helped in its invention. So in 2000, we had people already thinking about these topological qubits, and the program expanded in 2006. So we started Station Q at Microsoft. It's actually located in Santa Barbara. The first Station Q lab is in Santa Barbara on UCSB campus, actually. And there, initially, it was to focus on the theory behind this topological qubit. How does it work? How would you engineer it? If I had an experimental colleague, how would I go tell my experimental colleague to go build it, right? How would you do that? What materials do you need? What temperatures do you need? What environment do you need? Do you need a magnetic field? And so what Station Q has been doing is looking at how do you engineer and build this topological qubit and then eventually a scaled out quantum computer based on this topological qubit. So Station Q now is far more than just a lab at UCSB. Our program now expands to my team. I lead a team in Redmond, and we focus on the software and the algorithms, the applications. What am I going to do with my quantum computer, and how am I going to program it? What does the programming language look like? What does the operating system look like? What is the runtime? What is the compiler? How do I get my information, my mathematical formula, into that machine? And so we're building that stack, the complete stack in Redmond, and asking, what are we going to do with it? So we're also developing the algorithms. In Santa Barbara, of course, they're engineering this, looking at how would you engineer the device. And then now we have Station Q labs around the world in Copenhagen, Delft, and Sydney, as well as at Purdue, who are actually building and realizing these devices and realizing, starting to realize a topological qubit. Now, this requires a ton of very new physics. So it's pretty exciting, it's pretty cutting edge, and it has a lot of promise for solving the world's unsolvable problems. So a little bit more about this topological qubit. This is Ettore Majorana, Italian physicist. And in 1938, this really points to the origin of this idea of the topological qubit. In 1938, Ettore Majorana, he hypothesized that there was a particle that was its own antiparticle. So what does that mean? That means if those particles come together, they will annihilate. You won't be able to detect it. It has zero mass. And this is actually the basis of our qubit. So this thing, it's actually, we consider it more of a quasi-particle. This quasi-particle is what we're going to store information in and compute with. Ettore Majorana hypothesized that it existed in 1938, right? Quite some time ago. He disappeared within, I think, several months. It may have been a year or so after he made this hypothesis. He disappeared. He got on a ferry in Italy and never returned. So not only did we lose Ettore Majorana, we also never had seen, until very recently, this quasi-particle that he talked about. which people like to call the Majorana fermion after Ettore Majorana. So the man and the particle were yet to be, seen again, or seen in the first place. Now, this particle is this quasi-particle, this Majorana fermion that we base our quantum information storage around, is very, very important because it's a new way to store information using quantum mechanics that actually is more robust than the types of qubits we have on the landscape today. So the promise, the theory says that this information, this way of storing and computing information quantum mechanically, will be far more reliable and far more robust to errors and noise and disturbances than other types of qubits. So for years now, people have been studying things like ion trap qubits based on ions and superconducting qubits based on Josephson junctions. And these types of qubits are also, you can store and compute information, and we know companies that are working on these types of qubits, but their noise rate is not quite as good, and so you may need more of them. Now, this qubit, I mentioned the man disappeared in 1938 after hypothesizing about this quasi-particle. What's really exciting is that the proposals made by Station Q on how to engineer this system, well, we had our experimental colleagues, now part of our team, Leo Kouwenhoven at Delft. He took these designs and built them in his lab, and in 2012, he actually saw evidence of this Majorana quasi-particle. So if anyone's heard of the Higgs boson, right? God particle, big deal, high energy physics. This is like the God particle, the Higgs boson, but low energy, very, very cold. So finding the Majorana fermion is as big of a deal. This is a Nobel Prize winning moment for Leo, we think, right? You don't get a Nobel Prize until you're much older always, right? So, maybe in 30 years, 20 years, he'll get the Nobel Prize for this work. But it's as big of a deal as finding, evidence of the Higgs boson. So a big piece of scientific discovery in 2012. And now what's so exciting is this particle, this quasi-particle. There has been evidence of this quasi-particle in many, many labs around the world. Not just Microsoft labs, but many universities have become extremely excited about this area of physics, just as people are very excited about, the LHC, the Large Hadron Collider work and the science going on there. People are extremely excited about condensed matter physics because this is kind of a new era, right? Finding new quasi-particles, finding new evidence of very, very new physics. So it's very exciting, and we're really excited about it because it's the basis for a quantum computer. But as I said, all qubits are not created equal. And the reason we're pursuing this line of qubit, which requires all of this very new physics, right? It's not based on just the nice semiconductor technology we've had for the last 30 or 40 years. This is based on very new technology. But the reason we're going after it is because of its reliability. So if you think about scaling up, so when we think about a computer, right, we have some number of bits of storage in our computer. In a quantum computer, you can think of it similarly. We have some number of qubits in our quantum computer, ways to store and then compute on the information. So ultimately, we want to get to a very large quantum computer. So the number of qubits, right now in the news today, IBM announced they have a 16 and a 17 qubit chip. Right? So we're kind of on the left end of this plot on the x-axis. Now, if you ask about how noisy those qubits are, well, they're around 10 to the minus 3, 0.001. So what you can ask is, how are we going to get to a qubit in a quantum computer that can run really important algorithms? How are we going to solve the world's unsolvable problems? What size quantum computer is going to be needed to do that? And what we think is that at around 100 qubits, around 50 to 100 qubits, you can do something you can't do with any of your digital computers. You can't do with your supercomputer, no matter how large it is. That happens around 50 qubits. So on this plot, around that 100 mark, roughly, right, between 10 and 100. But to do something interesting, those qubits have to have some reliability. If I compute with them, they need to give me an answer that's going to mean something, right? It needs to be the correct answer. And so we need a low error rate. So what we want to do is we want to have lots of qubits that get better and better error rates, right? So if we have a good, reliable system, we want to be as far in that upper right corner as we can. And today, when we're talking about the types of qubits in the news, say today from IBM, you're looking at sitting somewhere, they have somewhere like here, right? So they're at 10 to the minus 3 error rate, and they have 10 to 15, now 16 qubits that they're going to make available in the cloud, which is super exciting, right? That we can play and that the qubits are scaling. We're seeing bigger and bigger chips. This is absolutely fantastic for our field and to show, quantum computers are actually scaling up. So they've moved kind of up to here. Now, to do something that we can't do, and to do a large problem, we still need to move up this diagonal. So what they're doing is starting here, and they're going to have qubits that sit between 10 to the minus 3 and 10 to the minus 4. Kind of fundamentally, those qubits are going to sit here, and then they're going to move this way, and they're going to use software to boost it up to a better error rate. So they actually overlay additional software and redundancy to get the higher error rate. With a topological qubit, the type we're looking at, where we're hoping to start is actually here. So the error rate is far better, and then and of course it's a little harder with this very new physics to start right here. So it takes, to get the first topological qubit takes a little longer as we harness this very new physics, and then ultimately then we would move to the right as we have more and more qubits. So there are different approaches, and the idea here with the topological qubit is it's intrinsic to the hardware, this better error rate. So ultimately, we want to move all the way here. Everyone does, right? We all want to move there, whether we're using software or hardware to get there. But the topological qubit puts us in a pretty good place already starting at this nice error rate. So let's look at what this really looks like. So here's your quantum computer today. This is my colleague, Charlie Marcus, Dr. Charlie Marcus. He is a part of our program, and he sits at the Station Q lab in Denmark at the University of Copenhagen. We have partnerships with universities. And he sits in this beautiful lab here. People like to note that this is very Danish, that they have this beautiful wood floor in the physics lab with brass hinges and poles. It's gorgeous. Very Danish. But here, the key is that this is where your quantum computer sits. And what you'll immediately notice, you have this cylinder here. And then you see all these wires and all of these boxes. That's all of the control required to control the quantum chip. Right? So lots of outside wires are coming in. It goes into this cylinder, and this is a shield. This is one of the coldest places in the universe, inside that shield at the very bottom. So this is a dilution refrigerator. Remove the shield, and then you see these copper plates. Each of these represent and achieve different temperatures, right? So we start, right now we're at 300 Kelvin. If anyone remembers their Kelvin conversions. So we're at 300 Kelvin at room temperature. And we stage down to get to the very cold temperatures where we run the quantum chip. So we start at 300 Kelvin, we go to 77 Kelvin, then we go to 4 Kelvin, and then ultimately you go all the way down to roughly 10 to 20 millikelvin. This is almost absolute zero, right? That's very, very cold. So it's pretty amazing engineering that we can engineer a system to get that cold, right, at the very, very bottom. And so the quantum chip sits in a puck at the very bottom of this, and then you put the shield on and you cool it. It takes about a day to get this down to that temperature, and then you can run your quantum chip. And you'll see all the wires. All of these wires are all of the signals that are coming from room temperature, and you have to get those signals down, not dissipate too much heat. You don't want to raise the temperature of the dilution refrigerator. So you have to be very careful in how many signals you send down. There's a latency involved there. We want to keep a fast clock rate. We have to think about the latency of the signals. So there's a lot of non-trivial control engineering, control electronics, classical computing, right? Non-trivial classical computing that you need to think about to control your quantum chip. Because after all, the quantum chip is essentially a coprocessor, right? It's a hybrid computer. It's part classical in the sense of all the control, and then part quantum, right? Your quantum chip where it does its compute, and then it sends information back to the classical system. The classical system does some, maybe computation on that, or sends the next signal to the quantum computer, and then you proceed. So it's a tight feedback loop between the classical environment and the quantum environment. But let's step in and talk a little bit more about why we want a quantum computer. Why would this matter? If this can't do anything interesting, then why are we going through all these gymnastics to build this machine? But the truth is that it can do some pretty amazing, it can solve some pretty amazing problems efficiently, much, much faster than we can imagine on our digital computers or our future supercomputers. So this includes areas like privacy and security, in energy, things in the environment. When we think about clean energy, we want to capture carbon, save our planet, big problems, right? And quantum computers can help us with those. Can also help us in artificial intelligence and machine learning. And then ultimately one can envision that a quantum computer could be another processor that you can access in the cloud. So already we see the cloud becoming more and more heterogeneous with GPUs, CPUs, FPGAs, and then now, right, even IBM has in the cloud a quantum chip. So we're already seeing this progression of the cloud moving towards having quantum computers online. So what will we use this quantum chip for? So here is one of the first, really important problems that were identified to being able to be solved faster with a quantum computer than a classical computer. So some problems are actually designed such that they are hard on our supercomputers, our cell phones, our digital computers. Here's one of them. So this is the RSA 2048 challenge problem. 2048, it's 2048 bits long, this number in front of you. Now, can anyone tell me the two prime numbers that I multiplied together to get this number? No? Okay, well, I didn't think so, because if you could, you would probably be, you might already be wealthy, but you would be extremely wealthy if you could solve this, because you could have hacked every bank there is out there, right? So this RSA, the problem of this number, asking what are the two prime numbers that multiply together to achieve this number, this is called factoring. And factoring is the basis of RSA encryption. Now, RSA encryption is the mainstay of e-commerce today. This is the predominantly used form of protecting your credit card, for example, of protecting your password, of protecting your bank account, right? It's encrypted when you go online and hidden, and it's encrypted into this problem so that if someone tries to, find out your bank account, they see something like this. And to break this, they need the prime numbers. It's a hard problem, what we refer to also as a one-way function. This is very hard, right? We rely on this today. So here's the amazing bit. Classically, this takes you 1 billion years with our best computers and our best algorithms to break. With a quantum computer, with a reasonable clock speed, now the clock speed can affect this, but it's 100 seconds to break RSA, right? So, all of the internet is based on this, right? So you might find a little relief that the governments around the world and many groups, even at Microsoft, are working on what encryption system we move to so that we have a system that's secure against quantum computers. We call that post-quantum crypto, a system that will still be classical, but a quantum computer won't be able to break, won't be able to attack. RSA, it can be attacked by a quantum computer. But there are systems, we believe, that can't be attacked by a quantum computer. And NIST, for example, the National Institute of Standards, is looking and actually has a call out right now as we speak to find these other encryption systems. And they're going to be heavily looked at and attacked, and they're going to see if it's robust. So you should feel a little better that we are looking and know of examples that should be robust against quantum attacks. But that's a pretty big gap, 1 billion years down to 100 seconds. And some people say, well, just make the key size larger, right? A 2048-bit number is the key size I showed you. We could go to a larger key size. Going to a larger key size doesn't help you. This is basically almost an exponential difference in the algorithm speeds. So if we look at the key size, so the number of bits, we saw the 2048-bit number, and then we look how long it takes to factor, to find those prime numbers. The quantum scaling of the algorithm for 2 clock speeds is shown in green, and the red star is the problem I just showed you. The classical scaling, the best classical algorithm we know, it's called the number field sieve. It scales like this yellow line. And you can see if I move to a larger key size, let's say I go all the way out to 10,000. Okay, that's beyond billions of years classically, but quantumly, we're looking at, okay, maybe it takes me a day, maybe it takes me a month. A month is still way too fast to break RSA, right? So we can't move to a larger key size. Now this is, it's fascinating that a quantum computer, something based on quantum mechanics, can break a problem that's really founded in number theory, right? That's pretty amazing. It's not like a physics, it doesn't feel like a physics-based problem. So I think that's pretty fascinating and pretty inspiring that these problems need not look necessarily like physics problems, where quantum computers can actually, be useful and apply. But let's talk about some of the physics problems. So Feynman, Richard Feynman, amazing physicist, a huge inspiration to us all. You can go back to his lectures, and you can go all the way back to 1959 and find comments of his around the fact that information is actually physical, matter is made of particles, and he talks and alludes to the idea of a quantum computer all the way back in 1959. Right? You think about the digital computers we had then, right? This is pretty amazing that he was already thinking about quantum computing. And in 1981, or early 1980s, he actually explicitly said, there are problems that are really hard in physics. Take Schrödinger's equation. You want to solve that. You want to simulate the evolution of Schrödinger's equation. It governs our quantum mechanical systems. It's actually very hard to simulate that equation and that evolution. And what Feynman said, he said, well, let's pair this with something quantum mechanical. Why are we pairing this and asking this large Hilbert space, this exponential size space, to try to fit into our classical digital world? Let's pair it with a quantum mechanical world, with quantum mechanical information and computation, right? He already was talking about a quantum computer being able to do that. So what exactly was he talking about? He was talking about the simulation of physical systems, evolving Schrödinger's equation. Now, why should we care about those problems? Well, actually, we're doing a lot of such computations already. If we look at supercomputing usage today, you look at simulating physical systems and the simulations running on, say, on the Department of Energy's supercomputers in the United States, here's what they're doing. They're running problems in materials science. They want to understand materials and properties of materials. They're running problems in quantum chemistry. What are the ground state energies of molecules? Understanding properties. This can help with something like, say, drug design. So almost half of the supercomputing usage today is actually dedicated to simulating physical systems, the exact area Feynman talked about in relation to quantum computers. So naturally, can quantum computers help solve these problems? Now today we know that they can. If we look at, say, finding the ground state of ferredoxin. So ferredoxin is actually a molecule that's used in photosynthesis, in energy transport in photosynthesis. So if we want to understand photosynthesis better, seems pretty important, right, for possibly food production in the future, or if we want to engineer that. So we may want to then understand the ground state of ferredoxin. Now, classically, if we try to understand the ground state here, it's essentially intractable. The time scale to get the solution, to get a number out that is the ground state energy of this molecule, is essentially longer than the lifetime of our universe. That's a really long time to wait for a solution. It's doable, right? I mean, technically that's doable, but none of us are going to be around, I don't think. So what we asked several years ago, my colleagues, my teammates, they said, well, let's see how well the quantum computer, the algorithm for the quantum algorithm scales. And so they actually we have a software system that allows us to simulate at small scale the quantum algorithms. And so we programmed this quantum algorithm. There's a quantum algorithm that's been around since the 2000s for solving this problem on a quantum computer. And it's what we call in computer science, it's polynomial time, right? So for us, that means it's efficient. And my colleagues programmed it and looked at the scaling. And they found that indeed it was better than the classical algorithm. 24 billion years. Well, that's, but it's polynomial. So if anyone is a computer scientist, polynomial, it's scaled like n to the 11, right? Degree 11 is not the degree you want to see in your polynomial when you're looking for a fast algorithm, right? We want to see n squared. We want to see n cubed. N is roughly 100 here. So we're talking 100 to the 11 is the scaling. Not great, right? But faster than the classical solution. So what happened is over the course of 3 years, having programmed this in our simulator, our team actually started taking piece by piece, digging away at this problem. And over 3 years found that they could improve the algorithm, optimize the algorithm, find some better mathematical bounds. And what's amazing is in 2015 showed that they could get it down to something that scales roughly like n cubed, degree 3, which when you plug in for this clock rate is an hour. Now this is a killer application, right? And the improvements they made are not limited to ferredoxin. The improvements made are at the algorithmic level and can be applied to many, many other systems, many other molecules, other applications. So this was a pretty thrilling moment, seeing that we could now call this really efficient. Still polynomial, but now this is a killer app. So what do I do with this algorithm? Ferredoxin is just one molecule. But why should we care about being able to solve this algorithm? Well, the applications of this algorithm include being able to study something like nitrogen fixation. Nitrogen fixation is actually the chemical reaction, the process for producing artificial fertilizer. We use something called the Haber process today. So the Haber-Bosch process is actually, it dates back to the early 1900s. We really haven't changed the Haber-Bosch process and the process of producing artificial fertilizer since then. With all of the computational advances, we're still roughly using the same process. But with a quantum computer, we can actually improve this. The Haber-Bosch process uses something like 3 to 5% of the world's energy, natural gas. That's a lot just for fertilizer, right? So can we bring that down? Can we make the process more efficient? And what we do on the quantum computer is we look for a catalyst. We actually study catalysts and their reaction and how do they improve the reaction pathway? How do they improve that chemical reaction for producing ammonia from nitrogen, which is nitrogen fixation? So we can actually develop and understand a catalyst, working with quantum chemists, to better understand what catalyst will enable us to do this efficiently. And we can do that with a quantum computer and with a relatively small, modest-sized quantum computer. Another area, again, building on the idea of catalysis, a great area for quantum computers. Let's identify a catalyst that helps us more efficiently extract carbon from the ambient environment. This would be a huge step, right? Right now, we mostly capture carbon at a fossil fuel plant at the point source. If we could do this more efficiently in ambient conditions, this could be a huge win, obviously, for our planet. In material science, another application for quantum computers is to study, basically study materials and ultimately study their properties. And you can do this far more efficiently, similar again to the scalings we saw in the previous slide. You're looking at maybe, a week or a month to get a solution. And this could help you identify a material that might superconduct at room temperature. That would be a huge deal. Why? Because it allows us to do things like lossless energy transport. I can have a solar farm in Phoenix. I'm from Seattle. It's not sunny a lot. I could maybe transport that power, losslessly all the way to some other area of the country. So this could be a huge win for clean energy. So again, you can study that on a quantum computer, and again, a modest-sized quantum computer. And then using a different type of algorithm that I didn't discuss in much detail, you can look at machine learning. In machine learning on a quantum computer, what we've already identified is that you can actually compute models more efficiently. So if you want to model data or users, you can compute those models more efficiently on a quantum computer. You can get more accurate models. And so one can imagine that machine learning will have, quantum machine learning can have a large impact on the type of models we're producing, how quickly we can train them, and how good they actually are modeling the data and users. So huge win for, say, speech recognition, right? Or, when you drive your car, you want it to learn well, So all of these areas where we see machine learning, it's pervasive across pretty much everything we're doing today. All of your products, your phone, your home, your car, machine learning is there, and quantum computing can improve those models. So I want to take a few minutes. We've covered the hardware, how we might build this quantum computer, how we are working on building the quantum computer. And we've covered why we care about a quantum computer, the types of problems, the world's unsolvable problems. But how does this all work? Right? I didn't say anything. I just told you, just believe it. It works. Okay, but it's pretty magical how this works, right? It's quantum mechanics. Really exciting stuff. So the idea in a quantum bit, right, this qubit, it can take on a different property, something fundamentally different than what your bit can do. So inside your computers today, we have bits. They're binary, 0 or 1. Your quantum bit, your qubit, it takes on what we call a superposition of 0 and 1. It's actually a vector, and I'll show you a depiction of this. Now, we like to say it's simultaneously in 0 and 1, but there are some great careful nuances to this, right? That it's really, if anyone learned about Schrodinger's cat, right? Schrodinger's cat was in a box, and it was, they say, it was simultaneously dead and alive. And when you opened the box, it was either dead or alive. So we don't really know what was going on when it was inside the box, right? But when we opened the box, it was dead or it was alive. Qubit. It's inside the box, and it's 0. When I open the box, it's 0 or it's 1. Right? That's what a qubit does. But it's kind of simultaneously in 0 and 1, right? Because when I compute a function on this bit, I actually get both results inside that box. But when I open the box, I only get one of them, right? That's the catch. So this qubit takes on this weird combination, right? A superposition of 0 and 1. Now, I can actually use this in a real system. Physically, I look at a quantum mechanical system and I can encode this. Let's say I have an atom, then the ground state of the atom could be the 0 state and the excited state could be the 1 state. And then I can quantum mechanically, I can apply operations and I can actually get it into this superposition state. Similarly, take an electron. I take the spin. I could have spin down, be 0, spin up, be 1, and now I can actually manipulate this state into, say, the superposition that we just saw, this idea of 0 plus 1. Now, digitally in our computers today, right, we have this 0 or 1, and quantumly we have this weird superposition. And these alpha and beta factors are complex numbers. Right? We have complex numbers in our information storage in this case. So classically, I'm at the North Pole or I'm at the South Pole. Quantum mechanically, if we envision that we're in a sphere, right, the qubit actually is anywhere on the surface of that sphere. That's the difference, right? That's why it's a little weird to think about it as 0 and 1. It's more apt to think about it as anywhere on the surface of the sphere. And the classical bit is either at the North Pole or the South Pole. So this is the difference, right? And now I can actually compute. Let's say I start at the North Pole with my quantum bit. I can actually then apply an operation like a NOT gate classically, and I can flip the state. I can go to the South Pole. Okay, that's pretty classical. What about doing something not so classical? I can start at 0. I can apply a transformation called the Hadamard gate, and I actually get to this position, which is this nice superposition state, something I can't do classically. So these types of operations are what I kind of string together to make a quantum algorithm. When I string many of these qubits together, it's very hard to visualize when you go beyond 1 qubit. Then you have a superposition over all of the states between 0 and 2 to the n, where n is your number of qubits. So here, with 9 qubits, I have all of the states from 0 all the way up to 2 to the 9 minus 1. That's a lot of numbers encoded in just 9 qubits. And in fact, what's really amazing, if I take 250 qubits, right? We looked at algorithms that operate on 100 qubits, 200 qubits, 1,000 qubits. 250 qubits. If I want to store that in my classical computer today, I need 10 to the 80 classical bits. So do you realize how many bits that is? That's more atoms than there are in the universe. That's a lot of storage. We're not going to be able to store that state anytime soon. But a quantum computer stores that in just 250 qubits. And today we already are up to, say, 15 qubits, right, as IBM announced earlier today. So we're getting there. That's pretty incredible. In general, n qubits, you need 2 to the n bits of information to store it. So just imagine if we're operating on an algorithm that has 1,000 or 1,000,000 qubits. That's a very large amount of information in that machine. Now, when we design our quantum algorithms, we take advantage of quantum interference. And this is something that's very, very different than what we have classically. Right? So if you've heard about the double slit experiment, right? If I had 2 slits in a wall and I started throwing a baseball at the wall, well, behind that wall, you're going to see the pattern when the baseball went through the slit, right? I'm going to see 2 lines. If I throw that baseball, if it makes it through that slit, I'm going to see a mark on the back wall right where that slit was. So one can think of it as, just shooting right through those 2 slits. But quantum mechanics is different, right? We have this wave-particle duality. If you've ever been in a swimming pool or a tide pool and you stick your finger and it creates a wave out, right? And someone else sticks their finger and it creates another wave. And when those waves interact, right, they kind of interfere with each other. And some get bigger and some get smaller. The amplitudes of the waves changes. That's quantum mechanics. That's like what's happening to our qubit paths. Some of these waves, if I start a wave and I have 2 slits, and I start another wave, those interact. And so I get a very different pattern on that back screen. And some of the waves cancel each other out, interference. And when I design my quantum algorithm, I hope that some of the paths through that algorithm, some of the computational paths, cancel each other out. And I hope that others, I design it so that others get amplified. And then when I measure it, the high waves are the more likely one to get out, that solution. And if that solution is set up properly, that will be the solution to my algorithm. It's very different. It's a different idea, different setup in terms of how you design quantum algorithms. Of course, there's no free quantum lunch. Unfortunately, I can't just take advantage of this amazing parallelism and this interference directly. I have to be careful in how I design my algorithms. I can't copy information, right? I don't know about all of you, but when I learned to program, sometimes I just copy bits around, and I copy vectors, and then I do a printf statement, right, to see if it was working. No printf in quantum computers. And I can't just copy my information to, send it to other, say, processors or otherwise. And I have an I/O limitation. I have to read in the data. Then I get into this large Hilbert space, this ability to have this superposition and all these states in parallel. But then I have to measure. I open the box. I see one of them. I don't see all. I don't get all the solutions at once. So I have all of this information in my quantum computer, but when I measure, I get one thing out, one state. And then I do it again, I get one state, right? So I can repeat the process, but quantum computing is probabilistic. It's a probabilistic algorithm every single time. So I also want to mention that I mentioned earlier that when we were looking at quantum chemistry algorithms, we programmed them. Right? We actually tested them and simulated them on small examples. So we actually have a software stack that we're building out, and we've released a version of it online on GitHub. So if you want to try out programming with our quantum programming language, and you want to try actually running some of these algorithms, we have a whole tutorial and set of examples on GitHub. And here, the idea, we have this whole software stack that you have your mathematical algorithm. You need to get it into the quantum computer. How are you going to do that? Well, you take your quantum algorithm, you write it in a programming language that's specially designed for the quantum computer because you have these weird, you have superposition, you have interference, you have no cloning. So we have to redesign what the programming language looks like. We happen to have embedded our programming language. Essentially, it's a domain-specific language embedded in F#, functional language. And then basically, we write out a whole compilation stack. So we've written parts of, we're building out the compiler. So we have a compiler that takes that quantum program and then basically maps it to a quantum circuit, eventually maps it down to instructions that you run on your quantum device. And you can send it to, say, your quantum hardware and actually run it on your qubits. Or in the absence of having quantum hardware, or even when we have, scalable quantum hardware, you're still going to simulate it in advance, right? You still want to kind of co-design your algorithms and your hardware and get feedback. How do I redesign my algorithm? How do I optimize it, right? As I mentioned earlier in quantum chemistry, we did a lot of simulating and then feeding back and re-optimizing the algorithm to get it compressed down to that killer application size. So this is a great platform, a great innovation platform, really for speeding up the process. I mean, arguably, if we had had software in the state we had it today when we were developing, when people were developing the transistor, arguably it wouldn't have taken so long, right, to get to a scaled-out transistor-based computer. So with software, we can actually innovate far more rapidly. And so we're building this out to actually control a real quantum computer. But it's also allowing us to develop all of the applications and algorithms. And so I just wanted to leave you with the software, because that's something near and dear to my heart. And then also, if you want to learn more about what we're doing at Station Q at Microsoft, you can find out a lot more information here. This is my amazing team of collaborators and colleagues. We're spread around the world. And we are just amazed by the promise of quantum computing. And we can't wait to revolutionize what we can solve today with these amazing machines. So thank you very much.